Now we'll do an example that has more min terms and see what other patterns we can find in the K-map to help us simplify. So we have x and not x. We have yz, yz bar, y bar, z bar, and y bar, z. All right, xyz, that's a 1 right here. xyz bar, that's going to be a 1 right next to it. We have x, y bar, z. So that's still the first row. Y bar, z, that'll be that last spot in the first row. Next, x, y bar, z bar. Okay, that means the first row is completely full now. What else do we have? We have x bar, y, z. So that'll be in that first position in the second row. X bar, y bar, z. So that'll be here. And finally, x bar, y bar, z bar, which will be that spot. Now, sometimes, you might lose track of what you're doing when you're recording stuff into the K-map. So let's see, I have 1, 2, 3, 4, 5, 6, 7 terms, and 1, 2, 3, 4, 5, 6, 7 spots filled in on my K-map. Okay, that makes sense. That means I'm probably good to go. All right. So there's a lot of ways that we could simplify this. We of course we want to simplify as much as possible. So rather than doing 1x2s and 2x1s exclusively, we can actually, in this case, we can group 4 at a time that are in a square like this, 2x2. So we'll start with this bunch. Now the goal here is to get the biggest of these shapes, these rectangular or square shapes that I'm using to collect the ones together. As you want to get the biggest ones possible, and you want to cover everything. Okay, so there's this 2x2 here. We actually have another 2x2. It might not be very apparent, but we do, because notice our principle was to change one literal at a time. And if we think of this as kind of wrapping around, from y bar z to yz, we are also still changing just one literal, which means you can think of this edge kind of wrapping around and being this edge, kind of like a game of Pac-Man where you go in to the right side of the screen and you magically appear on the left side of the screen. Or you could think of this as being a strip of paper and you are connecting these two edges to each other. So with that principle in mind, we can now circle another 2x2 group, which would be, this would be half of it, and this would be the other half of my other 2x2. Now all that's left is a lonely one. And technically I could circle that lonely one like I did in the previous example, but remember, the goal is to get as big a piece as you can to cover this, right? So I could circle these two ones. I could do this 1x2 situation here. I could do this 1x2 situation here. But I want to get the biggest pieces possible. I'm not allowed to do 3x1 or 1x3 because there's no rule that lets us do a simplification with three things. Everything is pairs of stuff. It's like the X or not X, Y or not Y, Z or not Z. Those are the things that reduce to one. So with that principle in mind, I'm not going to circle this one by itself. I'm not going to limit myself to just circling this 1 by 2 rectangle or this 1 by 2 rectangle. I will in fact instead circle this entire row. It'll be a 1 by 4 row. And that's going to give me a way to cover all the ones. So we want to cover all the ones. With the biggest pieces possible. And the types of pieces that you're allowed to use are things like, well, technically you can do 1 by 1, but that's not the best way to go. You want to always go with the biggest pieces possible. So 1 by 2, 2 by 1, 2 by 2, 1 by 4, 4 by 1, or possibly 2 by 4, etc. Depends on your diagram, how many variables you have, how many slots there are. So that's kind of a preliminary look at the general principle here. Now let's look at our final simplified answer. And notice, we're not doing like tons of algebra steps using those properties I mentioned earlier. We're using those properties in the background, but it's almost like we turned using those properties into this game of circling groups of ones that have a particular configuration and trying to get the biggest pieces to cover all of the ones. And these overlaps that you're seeing are okay. You don't want to overlap so much that you have extra stuff you don't need. But we're doing like the bare minimum of overlapping to get the biggest pieces possible. So what's our final answer? Well, we have 3 circled things, which means we're going to have 3 terms. So I'll just put 2 plus signs to separate them. What's this green part going to be? Well, what is this 2 by 2 thing? Well, notice we have X or not X. So that means X doesn't need to appear in this green min term. We also notice we have not Z or Z. So that means we don't really care what Z is, because either way, we have not Z or Z, which is going to give us 1. All we have left is Y bar. So this green term just becomes Y bar. Now this wraparound 2 by 2, let's see what's going on there. We also, in this case, have X or not X, which means X does not need to appear in the final min term. And then comparing these column headings, we have Y or not Y. So all we care about that's left is Z. And then finally, instead of a 2 by 2, now we have a 1 by 4 in purple. And notice we have every possible combination of Y and Z with negation or not negation. So this row being circled means all we have left is X, essentially. And you can verify that for yourself, that it's almost like we factored out X from these 4 terms. And so we have YZ plus YZ bar plus Y bar Z bar plus Y bar Z. And if you use distributive property and the unit property and whatever other properties you need, all of this stuff added together is just going to become 1. So you're going to have 1 times x, which gives you x as the last min term for the final answer.